Okay, so in this video, we will figure out whether the following series converges or diverges. But first, let us rewrite the nth root of 2 as 2 to the power of 1 over n. As always, the first question we ask is, do the terms of our sequence tend to 0 as n tends to infinity? So as n increases, 1 over n will approach 0. 2 to the 0 is 1, and so 1 minus 1 is 0. And so we see that the terms of the sequence we're trying to sum are approaching 0 as n tends to infinity. This does not prove that the series converges, but it tells that there is a chance that the series might converge, right? If the terms we were summing would not converge to 0, then they would be too large, and so by the divergence test, the series would diverge. But since the terms we are summing do shrink to 0 as n increases, as n tends to infinity, then there may be a chance that these terms are small enough to give us convergence of the given series. Well, we have to inquire, is this the case or not? Well, although this looks simple, this is also rather complicated, right? This does not look like any of our familiar simple series, namely p-series or geometric series. So the question is, what do we do? We're trying to get an intuitive feel for this function as n tends to infinity. We know it shrinks to 0, but can we get a better approximation? Well, if you think about it, as n increases, 1 over n shrinks to 0. So what we're really interested in, since negative 1 is a constant, is the behavior of 2 to a very, very small number. So let's now look at this new problem. We are interested in the behavior of the function 2 to the x, 2 to some number, and again, we care about the long-term behavior of this sequence, meaning when n tends to infinity, and so when 1 over n shrinks to 0. And so we care about approximating 2 to a very, very small power. So we care about approximating 2 to the x when x is very close to 0. And this is the fundamental question now. We are trying to simplify the terms of our sequence, fundamentally simplifying 2 to the x, but still obtaining a very good approximation. And this should sound familiar. We want to find a very good but simple approximation to a function near a fixed value of x. The answer is, of course, the tangent line. Near a point, the tangent line is an excellent approximation to a given function as long as we stay close to the point of tangency. So here what we're going to do is find the equation of the tangent line to the x at x equals 0. So here, the point of tangency, x0, is equal to 0. And if you remember the general result, near the point of tangency, here x0, a function will be approximately equal to its tangent line. And if you remember, the general equation of a tangent line at a point x0 is given first by the value of the function at this point, then plus the change in y, which is of course the slope of the function at this point, times the change in x. And this approximation, of course, is only good if x is very close to the point of tangency x0. And again, all we are recalling now is the general result of linear approximation. Near a constant value of x, the values on the function will be very close to the values on the tangent line. And the closer x is to x0, the closer the values on the tangent line are to the exact values on the function. Now, let's replace with this example where 2 to the x is our function and x0 equals 0 is the point of tangency. So we have here 2 to the x will be approximately 2 to the x0, f of x0, here which is 0, so 2 to the 0, plus the derivative at x0. Well, recall that the derivative of 2 to the x by the exponential rule is 2 to the x ln of 2. So if we evaluate now this at x equals 0, which is 0, we get 2 to the 0 times ln of 2. Times x minus x0, but as x0 is 0, times x. This of course simplifies, right? So 2 to the x is approximately 2 to the 0 is 1, so we get 1 plus x ln of 2. And since we care about 2 to something very small, in our case x minus 1, let's subtract 1, and we get that 2 to the x minus 1 will be approximately close to ln of 2 times x. And this is again if x is very close, in our case, to 0. And now we have the linear approximation of this function being a multiple of x, the multiple being ln of 2. And we know that the closer x is to 0, the better this approximation is. And so we can replace x in this approximation by any other quantity that is very, very close to 0. Well, we have such a quantity, in our case, 1 over n, right? So when n tends to infinity, obviously 1 over n will be approaching 0. So 1 over n is a very, very small number, getting smaller and smaller as n tends to infinity, and so we can replace x now by 1 over n. And so 2 to the 1 over n minus 1 is approximately, when n is very large, ln of 2 times 1 over n. And would you look at that? The terms of our sequence, which look simple and yet complicated, as they don't look exactly like something close to a p-series or a geometric series, actually, using the method of linear approximation, are very close to a constant multiple of 1 over n. And if we sum now these terms, this gives us, ignoring the constant multiple, a divergent p-series. So we now have the intuition, and we can use the limit comparison test. We can ditch the constant multiple of ln of 2, this really won't matter, and go instead for the simpler 1 over n. So intuitively, from the linear approximation, this series will be roughly, again ignoring the constant multiple, on the same order of magnitude as the p-series sum of 1 over n. So here p is equal to 1. So we have here a divergent p-series. This summation of positive terms, being a divergent p-series, will blow up to positive infinity. We now want to use the limit comparison test to show that this linear approximation is good enough to confirm that these two series, although looking very different, are on the same order of magnitude. Either both are finite, or in this case, both should be infinite. All that remains now is to find the limit of the ratio of the terms of our sequence. So here, of course, Bn will be 1 over n, and An, the initial sequence, 2 to the 1 over n minus 1. So we now find the limit, as n tends to infinity, of An over Bn. So An, 2 to the 1 over n minus 1, over Bn, which we took as 1 over n. And now again here we have two ways to tackle this, right? As n tends to infinity, 2 to the 0 is 1, 1 minus 1 is 0, 1 over n also shrinks to 0, so we have a 0 over 0 case, which we can tackle using L'Hopital's rule, or we could also use our linear approximation. If you divide both sides by 1 over n, then this ratio will be approaching ln of 2. So here we're going to use the linear approximation and say this is simply ln of 2, which is now, we know, a positive number. If you want, and I leave this up to you, if you're not convinced that the linear approximation will yield the right limit, as we have a 0 over 0 case, apply L'Hopital's rule, and in one step after you simplify, you will get the same answer of ln of 2, which tells us that an is approximately ln of 2 times bn. So if we sum the corresponding terms, then both of these series will be on the same order of magnitude, as this series will be a multiple of this one. And again, just for good measure, we can write it down. So when n is very large, an over bn is approximately the positive number ln of 2. And again, for large values of n, and so the initial sequence an will be approximately ln of 2 times the new sequence bn. Let's replace now by the explicit sequences. So 2 to the n minus 1 is approximately ln of 2 times 1 over n. And so we can squeeze in here the summation. So if these terms are really, really close to these terms, then the series in each case should be on the same order of magnitude. Again, either they will both be finite or infinite. And again, as ln of 2 is a constant multiple, we can factor it out. And we have, as previously said, nothing more than a constant multiple of a divergent p-series, and so this is equal to infinity. And so both of these now are in the same order of magnitude by the limit comparison test. And so since this series is infinite, then this series will also be infinite. And again, if you have a constant multiple times infinity, or I should say, if the result of a constant multiple times this series is infinite, then the series here must be infinite. So the initial series, therefore, must be also divergent by blowing up to positive infinity. And that is our conclusion. So the initial series diverges by the limit comparison test. And we can write this down. LCT for limit comparison test. And what's truly elegant about this solution is that we used a very simple and familiar approach of linear approximation to find a really good but simple approximation to this function. And what we obtained was remarkably simple. Although the terms of our sequence are complicated and look very far off from either a p-series or a geometric series, as it turns out, from a simple application of linear approximation, we can approximate our function, the terms of our initial sequence, as simply a constant multiple of 1 over n, which tells us that, again, intuitively, with the help of the limit comparison test, that the initial series is about a constant multiple, in this case ln of 2, of this simple divergent p-series. And so since both are in the same order of magnitudes, since the simpler series blows up to infinity, then so does the initial series. And again, the proof that we were indeed correct in making this assumption, this comment, was the use of the limit comparison test. And so the initial series diverges by the limit comparison test, but again, the beauty of our solution was to obtain a simple approximation to the initial sequence using a familiar method from differential calculus, namely linear approximation.